So, today we will discuss an algorithm to compute the weighted shortest path length between all pairs of points. Earlier we have discussed Dijkstra's algorithm, which was to compute the same quantity where one of the endpoints for all paths was fixed, namely S. So, one can compute this by running Dijkstra's algorithm for each value of S once, so running it n times. But today we are going to discuss another algorithm. Now, before we begin with this problem, I would like to discuss the same problem, but instead of paths we focus on walks. So, let me remind you, a walk is a sequence of vertices so say this is x1, x2, x3, x4, x5, again x2, x6. The sequence of vertices such that there is an edge between every successive vertex. So, it is possible that you may revisit a vertex or an edge more than once, while in a path you never revisit a vertex. So, it is clear that there are several more walks than paths in a graph. In a graph with finite number of vertices, number of paths can be finite. Cannot be infinite because there are only n factorial possible sequences of n vertices. So, one can have at most I factorial possible sequences, I equal to 1 to n, and some of them are the paths and others are not even paths. But in terms of walks, this number is in general infinite. So, for example, if I have a simple graph with only two vertices and an edge, so I can have a walk which goes from x1 to x2 and then back to x1 and again to x2 and so on. So, this can go on forever. So, the number of walks are infinite and the walks themselves can be unbounded in size. So, if I want to look at all possible walks and then determine the weighted shortest walk, then what is the relation between the two quantities? So, let us first talk about graphs with weighted edges and weights are non-negative. So, first we consider only the non-negative weights. Well, in that case, suppose a certain walk x1, x2, x3, x4, x5, x6, x3 and then x7. Suppose we have a walk which goes like this, revisits x3, comes to x7. Now, because the weights are non-negative, then let us compare the weight of this walk with the path x1, x2, x3, x7. So, clearly the weight of the path x1, x2, x3, x7 is going to be less than equal to weight of x1, x2, x3, x4, x5, x6, x3, x7. So, this suggests that probably a shortest weighted walk is likely to be a path. And this is true because whenever a walk revisits a vertex, so suppose a walk W starts at some x1, goes to some xk and revisits xk and then goes on, then you have a cycle here, and the weight of this cycle is non-negative. So, we can replace this by another walk W prime x1, which is this xk. So, this is say alpha, this is beta and this is gamma. Then we can write down x1, xk and so on, where this is alpha and this is gamma. So, I can cut off the cycle and I get this. The weight of this W prime is less than equal to weight of W, and I can go on reducing and eventually it will become a path. So, I can always find a path with weight less than or equal to this. It is possible that a walk which is not a path also have a minimum weight, and that will happen if the cycle involved or cycles involved have 0 weight. Apart from that, it will always be a path. And even if you compute such a walk in your computation, you can always remove cycles from that and get a path out of it. So, what this suggests is that in case the weights are non-negative, then computing the weighted shortest walk length between a pair of points is the same problem as computing weighted shortest path length between a pair of points. So, we can take advantage of this observation and replace this problem by the problem where we enlarge the search space and put walk here. Now, let us talk about the case, second case, where the weights may be negative. What happens in this case when we are searching the minimum weight walk? In this case, suppose let us take a simple example. Suppose there is a weight 2 and a -1 and 3, and this is x1, x2, x3, x4. The walk from x1 to x4 can be x1, x2, x3, x4, which is the simple path that we have. The another walk could be x1, x2, x3, x2, x3, x4, which involves this cycle. Note that this and going back, it is a closed walk. I can go on doing this. I can have x1, x2, x3, x2, x3, x2, x3, x1. Note that the weight of the simple path is 4. Over here it is 2, -1, -1, -1 and 3. So, it just comes down to 2. This is 0. Now, it will keep on decreasing. In fact, it will become unbounded, will go to -infinity. So, the shortest walk is not even defined in this case, even when there is one edge with a negative weight. So, clearly the problem cannot be solved for the shortest path by replacing them by walks. But what happens when you have directed graphs? So, let us take a case 2 minus 1 3. Well, the same problem is not going to arise because x1, x2, x3, x4, x1, x2, x3, x4 is a valid walk as well as path, but x1, x2, x3, x2, x3, x4 is no longer relevant because x3, x2 is not in right direction. So, we do not have much problem. Now, let us take another case. Let us say 2, 3, minus 4, 7, 6, 5. x1, 2, x3, x4, x5, x3, x6. Now, I have several walks now. I can go like this, or I can, well, the simplest thing is just going like that, x1, x2, x3, x6, or x1, x2, x3, x4, x5, x3, x6, or I can keep on adding these cycles inside this. So, there are infinite number of walks, but note that the weight of the successive walks increases. That is because the weight of the simplest path is 10, then if I add this cycle, I am adding 13 minus 4, 9 more weight, so it becomes 19. If I add 2 times, it becomes 28 and so on. So, in this case, the shortest walk is still a path. The problem will arise when suppose the weight of the negative, weight of the cycle is negative. So, let us say we have minus 7 here. In that case, the straight path, the walk without cycle has weight 10, and when I go through this loop, it is minus, so it is 5 because you are adding minus 5 to it, and you keep doing it. So, it will become 0, then minus 5, then minus 10, and it will go to infinity, minus infinity. So, the problem again arises in this case, and we can no longer solve the path problem by focusing on walks. So, what we notice here is that as long as graph is directed, I can allow negative weights when there are no cycles of negative weight. Then we can deal with the problem with by replacing paths by the walks. So, what we have decided is that we can replace this word by walk and go on and solve this problem. Now, this time, unlike in Dijkstra's algorithm, we are going to make one change, and we will describe edge weighted graph in the same fashion, but the weight function will be a function from E to a structure which we will call closed semi-ring. So, what is a closed semi-ring? This generalization is interesting, and it could be applicable in more than the real numbers. A closed semi-ring is a tuple containing these components plus and 0. Okay. This is a set of elements. These two are binary operators, the plus and the product operator, and these two are special elements of R. and they satisfy the following properties. That plus and dot related properties are that R is closed under these operations, that is R1 plus R2 belongs to R and R1 dot R2 belongs to R for all R1 and R2 in R. Secondly, the operation, both operators are associative, dot R associative, which means that is R1 plus R2 plus R3 is R1 plus R2 plus R3, R1 dot R2 dot R3 is R1 dot R2 dot R3 for all R1, R2, R3 in R. So, they are associative, and 0 and 1 are respective identities. Which means R1 plus 0 is 0 plus R1 is R1, and R1 times 1 is 1 times R1 is R1 for all R1 in R. And then we also assume that plus is commutative. And that means R1 plus R2 is R2 plus R1 for all R1 and R2 in R. Third property is that countable sums are defined. Which means for any countable collection of elements of R, if you take their sum is defined, which means that no matter how I associate them, this sum is uniquely defined. So, we can also state this as Ri, I belonging to some index set I, which is countable, it could be infinite. So, for all Ri in R. And lastly, yes, I belongs to capital I, you are right, for all, oh here it is, for I belongs to this and for all Ri in R. Yes, thank you. Last is the distributivity property, and which says that R times some Si, I belongs to I, is some R times Si and some Si times R is some Si times R I in I. These properties also hold, or this is equivalent to saying, or you can also say that sum Ri I in I1 times sum Sj j in index set j2 I2. Both these sets can be infinite as long as they are countable. This sum is R I S j I in I1 and j in I2. Okay, so these quantities exist. Anything that satisfies these conditions will be called closed semi-ring. So, I am going to, yeah. Here we have not assumed that. We have not assumed that 0 is not equal to 1. Okay. So, I will take some examples. Closed semi-ring. The first one is the Boolean ring. All properties that we have described are easy to see hold in this case. The infinite sum, for example, Ri plus becomes R1 or R2 or R3. If even one of these entities is 1, then this is 1, otherwise it is 0. So, it is well defined. Other properties are easy to check. Let us take the second example. Here the set is the set of non-negative reals. The plus operation is minimum. The product operation is the normal plus. I am assuming that plus infinity is a member of this set. So, plus infinity and 0. So, in this case, an infinite sum Ri is minimum of R1, R2, R3. Now, a particularly nasty case of this is, for example, say this is 1, this is 1 over 2, 1 over 3. If you consider this, this does not seem to have a minimum, but we stretch this idea and say that the limiting value of this, which will take to be 0. Although it is not an element in this, but arbitrarily close element to this is present in this. Other properties are again very easy to verify in this ring. Let me take a similar ring. But we do not restrict the numbers to non-negative reals. In this time we are allow all numbers. Then this also satisfies every property, but in this case, if you take a look at the sum, and if I pick, for example, 0, -1, -2 and so on, then this quantity approaches minus infinity. And note that a similar concept of arbitrarily close, we can't take the limit, because here there is always an element which is arbitrarily close to 0, but that is not the case here. So, this minimum does not exist. So, this is not a closed semi-ring, but we will use this particular ring, ensuring that wherever we come up with infinite sum, the sum exists. And a fourth example is on set of languages. Consider a symbol set sigma, then L sigma denotes the set of all languages on sigma. The plus operation is union, product operation is catenation, the two elements, special elements are the empty language and the language containing the empty string only. Okay. Here the catenation operation is as follows: given any two members L1 and L2 in L sigma, L1 catenation L2 is W1 dot W2. This is the catenation of two strings where W1 is in L1 and W2 is in L2. So, with this definition of the operator catenation, again verify that this is an example of a closed semi-ring. The problem with this ring is that typically infinite sums such as say Li anyway, the members of Li are generally infinite sets, and hence these are also likely to be infinite. And in computation usually we do not deal with infinite quantities. So, this will not turn out to be a useful ring for our application. Okay, so, now we have a graph where weights are associated with the edges, and the range of this weight function is a closed semi-ring. And now we want to compute the weight of the shortest weight walk in the graph. So, let us, because now it is no longer a real number, let us consider a walk. Let us suppose it is x1, a walk W, capital W is x1, x2, x3, xk, which may allow multiplicity of a vertex. But what is important is that there is an edge between xi and xi plus 1. So, we define the weight of, okay, I should use the small w, the weight of the walk W is the product of the weights of various edges this denotes an edge, this is the weight of that edge, which is a member of the closed semi-ring, and we have this operation defined, and remember it is a associative operation. So, I am not putting any brackets around it. So, this quantity is the weight of the walk given here. Okay. Now, we will assume that the vertex set is x1, x2, xn. I associate some index from 1 through n to the vertices of V. Then let us define a quantity, namely Ckij. Ckij is the sum. Remember, there is a sum operation in the closed-semi ring. Here. Is the sum of the weights of the walks, and these walks are the walks W from xi to xj. But there is one more restriction, and that restriction is that except for the first and the last vertex of the walk, all the intermediate vertices must belong to the set C1 through x1 through xk. So, we have to add that intermediate vertices belong to x1 through xk only. So, we have this restriction. Subject to this restriction, every walk qualifies here if it starts at xi and ends at xj. That sum. So, let us quickly take a look at what is this quantity for k equal to n in these examples. So, what is Cnij? When this is n, the restriction is lost, it has no meaning, because then it allows all possible vertices. Let us take a look at the ring R plus min plus infinity and 0. In this case, we are computing the minimum of the weights of those walks which start at xi and end at xj. So, this is Cnij is the weight of the minimum weight walk from xi to xj. This is precisely what we want to compute. Okay. This is the first example. Second, let us take a look at the Boolean ring. In case of the Boolean ring, we had the set of Boolean constants, the OR and AND operation, and 0 and 1. This is what the ring was. Now, what we have here is a graph G to start with, but in this case, what we will do is, instead of working with G, we will work on a complete graph which is denoted by Kn, which means the graph containing same set of vertices, namely x1 through xn, but every edge is allowed. So, this is nothing but xi, xj, or rather let me use some other symbol, xa, xb for x A and x B in V and A not equal to B. The complete graph. And we will define, to capture G, we will define weight for x A, x B edge to be 1 if x A, x B belongs to G, to the edge set of G, 0 otherwise. Note that in Kn every pair is an edge. So, we are assigning the weights in the following fashion. This essentially captures graph G inside Kn. For this particular weight set, the value of Cn ij will be the sum, which is the sum of all the walks from xi to xj, xi to xj, and we have weight of the walk. What is the weight of a walk in this ring? Well, every sequence of vertices is a valid walk in Kn. So, in Kn, x alpha 1, x alpha 2, x alpha 3 is a walk. But if this is the walk, what is the weight of the walk? It is easy to see that if all of these are edges in G, then and only then this will be 1, otherwise it will be 0. So, this means if and only if W is a walk in G, if and only if not, that is otherwise. So, it captures the fact that this is a walk in G when the value is 1, and when you are summing, you are essentially doing OR. So, this will be 1 precisely if there is at least one walk from xi to xj in G. Okay. So, C n I j is 1 if there exists at least one walk from xi to xj, 0 otherwise. It is easy to see that this is also saying if and only if there exists a path from xi to xj. Okay. This is the meaning of Cnij in the Boolean ring. Now, our primary interest is of course in the first ring, where we are computing the minimum, the weight of the minimum weight walk, which we have seen will be same as that the weight of the minimum weight path if we are dealing with undirected graphs and the weights are non-negative integers, or it is also the same when the negative weights are allowed in directed graph, but there are no negative weighted cycles. So, let us now talk about the algorithm to compute Ckij. Cnij for I, but we will compute actually all Ckij. So, the step 1 is to compute to initialize the value. We will do this computation by increasing index k here. So, we will begin with C0ij for I equal to 1 to n, for j equal to 1 to n, C0 ij. Well, this is the sum of all the walks from I to j, not allowing any vertex outside this collection. This is empty set. So, the only possible walks that can be counted here are the edges that start from xi and end up in xj. So, there will be a walk, one walk to consider, and that will be having the weight w xi xj. This is the only possible walk. This is one edge walk. Hence, this is also the sum of all the walks. And everything is fine except when I is equal to j. In case I is equal to j, we will have to separately set this. So, for I equal to 1 to n, you have a vertex xi. There are two possibilities, that you start here and with the empty string you stay there, that is a walk, or you have a loop. The loop has weight w xi xi. The weight of the empty string will be 1, which is the identity of the product. Remember, the product is the operation we use to compute the weight of the walk. So, we will set this C0 I equal to 1 plus W xi xi. Now, we are ready to compute the Cij for higher indices. So, we will put this into another loop for k equal to 1 to n, for I equal to 1 to n, for j equal to 1 to n. And we want to compute C k I j. Got to determine this. Now, to compute this, we have to see how this can be computed from the C values between all pairs of vertices, but the index here is up to k minus 1, because those are the values we have already computed. So, let us take a look at a walk from xi to xj. This is a sum of the weights of all the walks that go from I to j, and the intermediate vertices are allowed to be x1, x2, x3 up to xk. Let us take such walks and classify them, partition them into several sets. First, I will assume that all the intermediate vertices in this walk are from set 1 through k minus 1. We do not have any xk in this. Then we will consider those which have one occurrence of xk. Then all sorts of walks where there are two occurrences of xk. and so on. Collectively, these account for all possible walks that are of any interest here. Let us find out what is the contribution of these walks to this sum. Well, clearly the weights of the walks that fall in this collection, they add up to precisely C k minus 1 I j, because we never visit x k, we only restrict our visits to x 1 through x k minus 1. Let us take a look at the second type of walks, and we take this walk and split it into two parts. The weight of this walk is weight of walk xi to xk and from xk to xj. Okay, so let us find out what is the sum of those weights. All these walks start at xi, reach xk, and then start at xk and at xj. Let us suppose this is some walk W1 and this is some W2, and we would like to sum the weights of these walks. Weight of W1 dot W2. This dot just indicates this is a walk, this is not an operator, this is just the conjunction of two walks. But this is same as the weight of W1 times weight of W2, because the way weight was computed was the product of the weights of each edge. So, this is the weight of this walk. Now, we allow all possible walks from xi to xk, herein all walks from xk to xj. So, this can be written as some weight of W1 dot some weight of W2, where this is a walk W1 from xi to xk, visiting only x1 through xk minus 1, and here W2 is from xk to xj, visiting only x1 through xk minus 1. Okay, so, in the second type of walks, what we have here is the Ck minus 1 Ik dot Ck minus 1 Kj. Now, let us take the third type of walk. The third type of walk start at xi, go to xk, then revisit xk, and then get back to xj. So, by the similar argument, one can show that this type of walks will contribute Ck minus 1 Ik dot Ck minus 1 Kk dot Ck minus 1 Kj. This way we will have all successive terms coming in. So, we can now write down the value of Ckij in terms of Ck minus 1 terms. So, this will be C k minus 1 I j plus C k minus 1 I k dot C k minus 1 k j plus C I k k minus 1 dot C k minus 1 k k dot C k minus 1 k j. Dot dot dot. In general, the term will look like C I k k minus 1 dot C k k k minus 1 power p dot C k j k minus 1. This is one occurrence of C k minus 1 k k. Next time there will be C k minus 1 k k dot C k minus 1 k k and so on. So, that can be written as the square of this, the cube of this and so on, in general pth power of this, and this infinite series proceeds. Let us simplify this. This expression now looks like, let us write down as C k minus 1 I j plus C k minus 1 I k dot 1 plus C k minus 1 k k plus C k minus 1 k k square infinite sum dot C k minus 1 k j. This sum is written as C I j k minus 1 dot C k k k k k minus 1 star dot C k j k minus 1. This stands for this expression, this infinite sum. So, now I can simplify this expression and write this as C k minus 1 I k dot C k minus 1 k k star dot C k minus 1 k j. And now we can replace. This is the simple expression that computes the next level C expressions. Yeah.
Cij 0 should also. Ci2 j k minus 1.
I am sorry.
The path from I to j without using k.
Without using k is this. Oh, okay. I have not written that. That is C k minus 1 I j. That is right, indeed. So, the fourth step is just to output C n I j for all I n j. The time complexity, notice that this is order n square, this is order n. The problem with the computation of the complexity is that what is the time it takes to compute the star operator. If say it takes some time f, then the time complexity will be order f times n cube. Let us quickly take a look at what is f for our two examples. The Boolean example, in the Boolean ring, x star, which is 1 plus x square plus cube all the way, is nothing but 1 or x square or and so on, which is 1. So, this simply is replaced by 1, hence it reduces and simply it becomes C k minus 1 I k dot C k minus 1 k j plus C k minus 1 I j. So, that means here the time complexity reduces to order n cube. In case of the ring R plus min plus infinity and 0. The x star is the minimum of 0 x square, which is 0. So, once again this is easy to compute and the time complexity reduces to order n cube, because you do not have to do any computation here, it is just 0. Okay. The expression, in fact, let us write down, will turn out to be C k I j will be C k minus 1 I k plus C k minus 1 k j, okay, and so it is the minimum of the two, and C k minus 1 I j, it is the minimum of these two. This is that simple. And one more last comment is, when we have this structure which is really not a it is no longer R plus, it is R min plus infinity and 0. If you notice, the only infinite sum that we deal with is this. So, in this ring also it is well defined, and x star is again, it is nothing but the min of 0 x . Now, the problem will arise if this quantity is negative. If it is non-negative, then it is well defined. So, this weight also works as long as x is non-negative. And what is x? In our case, x is C k minus 1 k k, which is the total sum of the weights of the rings that start, walks that start and end in k. So, these are the closed walks. Hence, this is okay, because we have assumed that in our examples all the closed walks have non-negative weight. So, as long as this is the case, this is well defined, x star is well defined, and the time and it reduces to just this case, and its time complexity is order n cube. So, the last point I want to make is that this approach, unlike Dijkstra's approach, allows us to deal with negative weights as long as cycles do not have negative weight. But on the flip side, the time complexity is n cube, but if you run Dijkstra's algorithm n times, then the time complexity would have been n times n plus n. which will compute also all pair shortest paths. And note that m in the worst case is n square. Hence, in the worst case it becomes n cube, there it is always n cube. So, that is the positive side for Dijkstra's algorithm. Okay, that is all. Thank you.